Hi, welcome to Smart Physics, and this is chapter 26. I'm just explaining how the problems have been worked out. And chapter 26 is about direct current circuits. Now, the basic law in electricity is, of course, Ohm's Law. And in this chapter, you have an extension of Ohm's Law, which is Kirchhoffs laws. And you're going to see how Kirchhoffs laws are applied in the circuit to solve for the current in different branches of an electrical circuit. In this question, you're actually given 9 1-ohm resistors, and you're asked to connect them in such a way that from a 9-volt cell, you should be able to get 4 volts. So the way to do that is connect all the 1-ohm resistors, line them up in series with each other. And I've not shown the complete picture. This is about 4 of those resistors, and this is 5 of them. So if you take a connection from these 2 points, if you tap it off from 1 and 2, the voltage drop across this is going to be 4 volts. And if you tap the connection between these 2 points, then it's going to be 5 volts. And the reason is because the total resistance is 9 ohms, and therefore the current is 1 ampere. And when that current flows across these 2 points, you're going to get 4 volts. And when the potential difference across these 2 points is going to be 5 volts. Because voltage or potential difference is the product of current and resistance. Now, this kind of arrangement is called a voltage divider arrangement. And if you have a movable key, you can actually move this point along the resistor combination, and that way you'll be able to get whatever voltage you want, all the way from 0 volts to 9 volts. And this is an important arrangement. And here's question 2, and I think because the question comes later, there are 8 light bulbs, and they're all connected in series to a 110 volt line. What's the voltage across each bulb? Okay, because they're connected in series, you know that the voltage is shared, and therefore the voltage across each light bulb will be 110 divided by 8. And to find the resistance of each bulb, you just got to know the voltage across each one of them, which is 13.75, and divided by the current drawn by each one. It's given as 0.42 ampere. So you get the resistance of each light bulb. And then the power is the product of voltage and current. The voltage across each one is 13.75, and the current drawn by each one is 0.42. So the power is 5.78 watts. In question 3, you have a circuit as shown here. And when you try to analyze a circuit like this, you need to think in terms of currents in order to figure out if it is a series connection or a parallel connection. Alright, to make it clear, the current starts flowing from the positive. Of course, it flows from the positive to the negative. So when the current reaches here, it's going to split into two parts. One part going through the 680 and the other part going through the 820. This means that the 680 and the 820 are connected in parallel. Okay, so that's how you figure out. But then you see that the two parts that have split, they will recombine here. And the entire current that started out from here will now flow through the 960. Which means that once you get the combination, the total resistance or the equivalent resistance of these two, that combination resistance is going to be in series with this. So that is the way to figure out how resistors are connected. So let me call them R1, R2 and R3. R1 and R2 are in parallel as I explained. And the quick way to find out the total is product divided by sum when there are only two resistances. And once you get that, I've done it in all in one step. Once you get that, because that total resistance is going to be in series with the 960, you just got to add it. So that's why I've added R3. So that is the total for the parallel combination, and then you add the R3 because it is in series with it. So that gives you the total resistance, and then to find the current, divide the voltage by the resistance. Now the voltage across 960 ohms is going to be the current that flows through it multiplied by its resistance, and the entire current flows through it, so you just multiply that entire current with its resistance. You get the voltage across 960, and the voltage across 820 and 680, they must be equal, because whenever you have components connected in parallel, the voltages are the same. And it should be the difference. So 12 take away 8.65, that is 3.35 volts. And now to number 4, you have a circuit like this, and I'm just labeling them so it's easy for me to explain. Okay, now again take a look at this. The current starts flowing from here, that's the positive, and it reaches here. Definitely when it reaches here, it's got to split into two parts, right? Okay, and that current that reaches here again has to split into two parts. But look at that, the current that splits here and flows through R1 is exactly the same current that has to flow through R2. Now since the currents flowing through R1 and R2 are the same, that means R1 and R2 are in series with each other. And then that total combination is in parallel with R3. Let us take it off from there later. So R1 plus R2, because they are in series, in parallel with R3. That is 2R in parallel with R, which is 2R times R by 2R plus R. Now the total of R, to find the total of 1, 2, 3, 4, this total is simply added to R4. Why? Because that combination is in series with R4, the same current that flows through this. Let me stop that there. Because remember that the current that split here into two, of course, recombined here, didn't it? And so whatever split here, that total current is going to flow through R4. Therefore, the current through R4 is exactly equal to the current that flows through this combination. That's why R4 is in series. Okay, and that's how we got 5R by 3. But then when you include R5, you see once again that the current that reaches here is now going to split into two. One through R5 and the other part through R6. So this time R5 is in parallel. Okay, so 5R by 3 is in parallel with R5. So you have to go for the product by sum again. Do the math carefully. And once you put that combination here, you see you get the total finally of all the 6 resistances just by adding that to R6, because that whole combination is definitely in series with R6. So the final answer is 13 by 8 R. And hopefully you understood. Number 5. You have two resistors of 3.8 kilo ohms and an unknown resistance connected across 110 volt. First they are connected in series with each other, and then they are connected in parallel. And in each case the power consumed is not given, actually it's compared. It says that the power consumed when they are put in series, that is PS, is 1/4 of the power consumed when they are put in parallel. Important thing is that in this case the voltages are equal across both because it's a parallel connection, and therefore since the voltage is the same, we'll use this relation for power. The rule is that you always have to use the equation that has one constant and then the other is the variable that the problem is talking about. And therefore, substituting in both cases, you find that the total resistance in series is 4 times the total in parallel. And what is the total resistance in series? Isn't just the sum of the two? Yes. So it should be 4 times the product by the sum. And now it's just a matter of solving that equation. You end up with a quadratic equation which fortunately can be solved by splitting the middle term here as I've done. And therefore you understand that the resistance must be 3.8 ohms. I mean kilo ohms, because I had kept it in kilo ohms. And now finally you see the question 2, which anyways I had explained. Brings us to number 6. Now this is where you have to apply Kirchhoffs laws, and when you apply Kirchhoffs laws, you have to carefully look at the circuit and decide, okay, KCL is Kirchhoffs current law, according to which if you look at this diagram, you have I1 and I2 flowing away, I3 is coming into this junction. Therefore, I3 is equal to I1 plus I2. And then when you try to apply Kirchhoff's voltage law, in the top mesh, as I can see, in the top mesh, and you're going around in the clockwise direction, let's say you start from here and the current flowing is I1, And since you're going in the direction of the current, it's negative 34 I1. And then as you come here, you are going from the negative to the positive of the battery. So it's plus 45. And then again, you're going in the direction of the current. So it's minus 47 I3. And again, minus 48 minus 1 I3 minus 47 I3. So I've put them together as minus 48 I3 is equal to 0. So minus 34 I1 plus 45 minus 48 I3 is equal to 0. Okay, now when you look at A, H, D, E, F, G, A. So what's that? So that's A, H, D, E, F, G, A. I'm looking at this. Okay. No, I couldn't see it properly. I'm sorry. I'm actually applying it to this circuit because it's AH is here. Okay, so I'm taking the outer one. That's why you have minus 34 I1 again. And here, when you go down to this, the current through this branch is I2. And you are going down while the current is going up. Okay, because you decided to go down like that, look, in the clockwise. But actually the current through that resistance is going up, and that's why it becomes plus 18 I2, and then again you have plus 1 I2, so that's 19 I2. And then when you go across the battery, you're going from the positive to the negative, so it's negative. All right, so see that here minus 75 because you're going from positive to negative. So you have your three equations, and you have to solve these three equations in any way you like. I have rearranged the equations, and I'm substituting for I2. So I can eliminate I2. That is the equation into which I'm substituting. No, actually I'm making I3 the subject there. So I have an equation in I3 and I1. But I3 is I1 plus I2. And so I'm using I3 is I1 plus I2. All right. I've carefully shown you what I've done. And then I get the value for I1, which I substitute back into that equation to find I3. Kind of running out of space, and then get I3. Once you get I3, put it back into one of those equations and get I2. And you can solve using matrices or use simultaneous elimination method or whatever, but getting the equations is the most important part. Sorry for that. And this problem again continues. It actually asks you to find the potential difference between A and D. Potential difference is current multiplied by the resistance of the branch. And you have to look at AHDG. Since you're looking at AHDG, sorry for the disturbance, and ABCD, from ABCD 48 I3 minus 45, and from AHD you have 29.27. You may want to go back and look at the circuit again. AHD and ABCD. Understand that AHD is this part and ABCD is this part. So what I did is actually taking the potential difference here by multiplying current I1 with this resistance, and then finding the potential difference here by multiplying I3 with the total resistance here, and also including the battery there. So that's what you find. You look at this carefully, you see 34 I1, and then you see 48 I3 minus 45. So you got 29.27 and 29. And then the terminal voltage is 75 minus the current flowing through 1. Okay, so you got to look at that really carefully to understand. You may want to write that down. Now let's see in this circuit, which looks much simpler, when you apply Kirchhoffs laws, as you can see here, you're going to get plus V3 minus 18 I2 is equal to 0, from which you can find I2. And then when you take the outer loop and go this way, as I've shown, you get 9, or on this one, 9 plus 18 I2 minus 22 I1 is 0. I'm looking at this one, okay. So 9 plus 18 I2 minus 22 I1 is 0. And so I get I1 and I2. That's just a simple application of Kirchhoffs laws in a much simpler circuit. Here you have another circuit. Currents are I1, I2, I3. It doesn't matter how you label the currents because the final answers will be the same, but I just put it in such a way that it appears as I1 coming in, I3 coming in, I2 going out. So I2 is equal to I1 plus I3. And then when you look at ABEFA, which is ABEFA, you're going that way. So when you're going that way, okay, if you're going, I think I've written the equation going this way. Okay, so let me go this way, because whatever direction you go, you get the same equation, remember. When you go this way, you see you're going to the positive, so it's plus E1 along the direction of the current, so minus I1 R1 along the direction of the current, so minus I2 R2 is equal to 0. Okay, those are the values. And then in BCDEB, again, if you go this way, plus E2 minus I3 R3 minus I2 R2 is equal to 0. You have two equations now. You will have to, actually you have three equations and you need to substitute and solve. That was I3. Well, I'm solving in my own way. I multiplied by 35 divided by 25 just to get rid of I3 when I add the equations. But you can do it your way and get the answers. Once you get one of the currents, you can substitute into the other equations and surely you can find the other currents. So those are the three currents that flow in this case. Number 9 is charging a capacitor through a resistance, which is given by this equation. Q is Qm, which is the maximum charge, times 1 minus e raised to minus t by tau. Now here tau is the time constant, which is RC, okay? So you can write it that way. And the problem talks about potential energy. Potential energy is Q squared by 2C. And when you substitute you can see that this is going to be the maximum potential energy, so I put it as UM. And the problem says that the potential energy is 75%. So that's why you have 0.75 there. And now you just have to be careful when you solve. Take the 1 to the other side, get that number, and on the other side, in place of exponential, you can put natural log and then solve for t. You will get 2.01 times the time constant. Now you see the question, how long does it take for the energy stored in a capacitor in a series circuit to reach 75% of the maximum value? And again, the questions are coming up later because I added them after I did this video. It was not there before. Now that brings us to the last question. And I want you to see the question first, so all of it together. Here it says the RC circuit shown has a resistance of 8.7 kilo ohm, capacitance is 3 microfarad, capacitor is at a voltage at zero, t is equal to 0 when the switch is closed. It doesn't say the voltage is 0, it says it is at a voltage. How long does it take the capacitor to discharge to 0.1% of its initial voltage? So this is about discharging, and for discharge the equation is a little different in that there's no 1 minus, and if that's the equation for charge, then because charge is proportional to the voltage, the equation for voltage will also be the same because the C's will cancel out, right? And so you substitute it. It says 0.1%, which is 0.001, and then it's just solving that very carefully. Make t the subject and solve for it. You get 0.18 seconds, and I hope this video is going to be really useful for you to study for the exam. Thank you.